All right, now we're going to do the second part of chapter 2, and these are the topics. We're going to go over energy, how energy is measured, types of energy as well, calories and foods, and then we're going to end with changes of state. So here we're going to be doing some math, especially when we're talking about measuring energy and calories and changes. First of all, energy and matter. Energy is the ability to do work. So, you know what it's like when you don't have any energy, you can't do any work at all. So it's the ability to do work. You see this person here climbing up some part of a mountain. Not something I would want to do, but good luck to you if you want to do it. Okay, work is done when something is moved a distance. But what work is this climber doing? Well, she's moving herself a distance. So the more she weighs and the bigger the distance she moves, the more work she's doing. Now, there are different types of energy. Two major types. The first type is called potential energy, and that's energy that's stored. And we think of like gasoline has a lot of potential energy in it. Coal and oil have high amounts of potential energy, whereas wood has much less potential energy. Kinetic energy is energy of motion. What it really is potential energy has been converted to kinetic energy. So it's really energy that we're using to do some work. So we have potential, stored energy, and kinetic energy. The units for measuring energy are calories and joules. And here are some conversion factors. 4.184 joules to a calorie. 1 kilojoule is 1,000 joules. Remember, a kilo of anything is 1,000 of the basic unit. And a kilocalorie is equal to 1,000 calories. Now, a calorie is an old unit that's actually based on water. And a calorie is the amount of heat needed to raise the temperature of 1 gram of water 1 degree centigrade. So a calorie is defined in terms of water. And again, that's something that we use in this country, but many other countries don't use calories. Here are some examples of energy use. It's measured in joules, but that's not that important for the chart. So what we want to check out are some of the differences here now. You see them all in powers of 10. Even when you sleep, you use up a lot of energy. A lot is relative, of course, but this is the smallest amount of energy based on the chart. And you can see as you go up, 10 to the 6 joules, a million joules, for one serving of pasta or a donut, or the energy needed to bicycle for an hour. I don't know about the pasta or the donut. When I eat pasta, it looks like it's a lot more than one donut would be, but you never know. Okay, energy from a gallon of gasoline, energy use of one person in a year, solar energy reaching the Earth every second. Keep going up, energy consumption for a year in the U.S., world reserves of fossil fuels, so that's why we're going to run out of them at some point. Energy radiated by the sun per second. So the sun gives off a lot of energy, but it's not all hitting the Earth. Okay, converting units. How many calories are obtained from a pat of butter if it provides 150 joules of energy when metabolized? So we're really asked to go from 150 joules to calories. So we just need that conversion factor, which is 1 calorie equals 4.184 joules. Now, why don't you pause it right now and try to solve this one yourself before you see the solution, because everybody should be able to do these simple conversions. So remember, it's whatever you're given, you're starting with, whatever you want to end with there. Here it's going to be calories, and you're going to write the conversion factor as a fraction. So you might want to pause it for a sec, write your answer, and then you'll see the solution. All right, here's the solution. See, we have the 150 joules is what we're given, multiplying it by a conversion factor. Whoops, let me go back here. And we would be, I don't want to always do this, we would be canceling out the joules. Just cancel that right out. Okay. So, how do we get energy from foods? Well, here are some different foods we have here. We have some pies and cakes. We have a turkey. We have beer and some nuts, it looks like. Well, we get energy from them when we change these substances from high potential energy that they possess to low potential energy. And we get the difference coming out as energy and work. So this is how it works. We eat high potential energy foods. The energy comes out as heat and work. Now, we don't want all our energy released as heat. We do for heating homes maybe sometimes, but we want a lot of the energy to be released as work so we can move things around and build new structures. Now, all of these foods produce these waste products. So we make CO2 and water from all these foods, and that means that all of these foods contain the elements carbon, oxygen, and hydrogen. Now heat's a little bit different. Some people think heat is like temperature, but it isn't. Heat is really molecular motion. So you remember the Kelvin, Kelvin temperature scale, we talk about that's based on molecular motion. So how do we calculate heat? Again, remember, heat is not measured by temperature. So in order to calculate heat, we have to use something called a calorimeter. Here is an example of a styrofoam cup calorimeter. And you notice we have a material down here. Here's a block of something that we've heated. We put this block, we would have weighed this first, and then we'd heat it, and then we drop it into a known amount of water that's in this styrofoam cup. We have a thermometer in here to note how many degrees the temperature will rise from that hot block that we dumped in there. And so we have to know how much water we have and what the temperature change is. The more water we have in the cup, the less of a change we would see. We have to have it covered now to keep all the heat inside it. So that's our coffee cup calorimeter. So we use a calorimeter to actually measure heat. Now here's a problem we're going to investigate a bit. Let's say we have a liquid, 250 milliliters of a liquid at 50 degrees, and a smaller amount in another flask at 50 degrees. So they're both at the same temperature. Now the temperature of the room, which is here, temperature is 25 degrees. Will the temperature of the liquids change over time? What do you think? Will both flasks release the same amount of heat as they cool? Now what's going to happen is, we know that these flasks will change temperature because they will eventually become the same thing as the air temperature. So heat always flows from where it's more intense to where it's less intense. So because the temperature of the fluids is greater in the flasks than the air, the temperature of the flask will drop as they lose heat to the air, and the temperature of the air will rise. Now normally there's so much air around us that it's hard for us to notice that increase in temperature unless we really have a lot of heat coming up. Now will both flasks release the same amount of heat as they cool? What do you think? Well, how could we calculate how much heat they would produce? What do we need to know? So and here's our formula. You want to jot this down now. We need to know the mass of the substance that's going to be releasing the heat. We have to know the temperature change it's going to undergo, and we have to know a property called specific heat, and that tells us whether the substance will release a lot of heat or a little heat. So all materials have a property called specific heat, just like they have a property like density. Now I can shorten the formula instead of writing all these words by writing M for mass, delta T, which means change in temperature. I'm just going to shorten specific heat to this so we know what it means. Many times they'll use a small letter for this, but I don't want to throw that in here. Okay, so this is the definition of specific heat. The heat needed to raise a temperature of 1 gram of any substance by 1 degree centigrade. Here are some specific heats. And the one we want to note all the time is water. You see the water down here. Now the specific heat has a funny looking unit. It's calories, remember calories is unit of heat, per gram per degree, or joules per gram per degree. Now all these numbers look pretty small. In fact, water, on this list, water has the highest specific heat. So what does it mean then? It means it takes a lot of energy to raise the temperature of water. We notice that when we heat water on a stove, it can take a long time to get that water to boil. But it also means that the temperature of the water will drop slowly as well. That's why a cup of coffee will stay hot for a while. Yet the stove, where you cooked it on, or you heated it on, will drop in temperature much quicker. So you notice that metals have much smaller specific heats, which means they heat up quickly and they cool down quickly. So let's take a look then at this problem here. We have gold at 50 degrees, 100 grams, is becoming 25 degrees, so it's losing heat to the air. Aluminum, weighing the same amount at the same temperature, is going to become aluminum at 25 degrees. So what we see here is both metals weigh the same, and both metals are going to undergo the same temperature change, which is 25 degrees. It just happens to be the same as this, but that doesn't matter. So the temperature change is the difference between the temperatures, and we always want a positive temperature change. So we're going to get 77 calories from the gold as it cools down. And the aluminum cools down, we're going to get, wow, look at all that heat we're going to get from the aluminum. Why do we get so much more heat from the aluminum than the gold? And yet both metals weigh the same and they underwent the same temperature change. So to see the difference, we would see that we really have to use their specific heats. So this is how we would do it out. Now for the gold, here's my formula. I replace it with the mass of gold, which is 100 grams. This is the temperature change, and that's the specific heat of gold. So you notice how the grams will cancel, and the degrees centigrade will cancel. So I'm going to get calories for an answer, and that's how I get my 77. Now for the aluminum, same formula. I make my substitutions. I cancel my units. They go to grams. They go to the degrees centigrade. You get calories for an answer. Now the difference in this is really the specific heat. Look at how much bigger the specific heat of aluminum is than the gold. So that's a 3 and that's like a 21. So that means that aluminum has 7 times the heat capacity of gold. So aluminum is a good insulator. You know, people used to put aluminum sidings on houses. Okay, so you can see that we get 535 calories. So you're going to see problems like this in the book where they ask you to calculate the heat that'll be released or absorbed when a change like this happens. And we'll do some of those in class. Now we're talking about water. So how much heat is needed to raise the temperature of 500 grams of water from 25 degrees to 100 degrees? So we want to use that same formula we had in the last example. So heat equals mass of water times the temperature change times the specific heat. I make my substitutions. Mass of water, 500 grams. The temperature change is going to be, it's 100 minus 25. So that's where I get my 75. I want to point out to you, here we're talking about raising the temperature of water, but if I was talking about water cooling from 100 to 75, 100 to 25, the 75 degrees would still be the change in temp. So the change in temperature has to always be a positive number. Okay, we can cancel out our units. Get our answer to go to grams, degree centigrade, and there we go. That's a pretty big number. So that's really too big of a number to have. You either want to put this in scientific notation, or maybe want to convert it to kilocalories. So kilocalories might be the way to go. So my conversion factor, of course, is 1,000 calories to a kilocalorie. And when I set that up, I get 37.5 kilocalories. So this is really the proper unit. So even though it didn't specify a unit, we want to use a unit that gives us a number, between 1 and, maybe 900 or so. Now, energy and nutrition. Here we're talking about food calories. They're calling it a nutritional calorie, which I guess means a food calorie. And we just use these in the United States. This is what you want to note, though. A food calorie, 1,000 little calories. A food calorie is a kilocalorie. Sometimes you take the word calorie and just make it CAL. And then you see we have 1 calorie, 1 food. This should be probably a little c, not a big C. Put that, change that a bit. It should be little c is this many. Oops, wait a minute, forget that. Yeah, that's right. Yeah. This is 4,184 joules. Okay, out of all these things, the one you want to remember this guy here, and you want to remember this one. We probably won't be changing these too many times. If you look over here at your snack crackers, you see this is the typical thing for you see on different foods that are processed. And notice to give you the calories, 120 calories right here. And they even have kilojoules, so they're doing the conversion for you. So they're telling you they sell this probably in Europe. Calories from fat, 35. Kilojoules from fat. So roughly, 4 times, if you look at it, 4 times the calories will give you the kilocalories roughly. And then we have a breakdown like this. Amount per serving. 14 crackers per serving. I don't know. Probably little crackers. It's hard to eat 1 serving. So here we have the conversion factors that we're going to use when we answer questions about foods. So carbohydrates, sugars and starches, produce 4 kilocalories of energy per gram when they're digested completely. Fats produce more than twice the energy per gram. The name for fats is lipids. When fats are digested. And proteins, if you notice, proteins and carbs produce the same energy per gram. Now, for the most part, we need proteins for building things. So you want to make sure you get plenty of protein in your diet for production of muscle and amino acids. And so carbohydrates mostly used for our energy. Fats are used for energy, but also for structure. And if we look at these, this will tell us pretty much the amount of energy that's produced. And you notice it's per gram of the different foods that we have here. So a banana, medium banana, 26, I don't know what medium is, but 26 carbohydrates, 110 kilocalories. This would be the food calories. So we can see which one is the most. Look at way down here. What do we have? A steak. A lot of protein in the steak. They have also a lot of fat. So, you want to eat a lean steak because there's so much fat with it. Unfortunately, the fats were all the flavors. What else do we have here? Milk. 4% fat. Well, whole milk is more like 3%, so we're up a little bit high with that. Non-fat milk. This would be like skim milk. Still, you get, because what you have in there, you have lactose, you get milk sugar. So it's still, the amount of energy is this is just pretty much double that. So if you're thinking that you should drink skim milk because you're on a diet, see, the energy difference isn't much unless you're drinking a lot of milk. And raw carrots, I don't know why anybody want to eat those. I don't see any potato chips on here. No, I can see my baked potato. I was like that. Notice this is minus anything else. Okay. So, could you figure this one out? How many calories are in a cookie that contains 2 grams of protein, 20 grams of carbs, and 10 grams of fat? So you want to pause the video at this point in time and use those amounts we saw a moment ago to figure out what's the total amount of energy in a cookie. And then we'll come on back and you can check the solution. Okay, here's the solution. So 2 grams of protein times 4 calories per gram, we get 8 calories. 20 grams of carbs times 4 calories per gram, and we get 80. And then now for the fat, see, fat gives us the most, 90 calories. So we just have to add them up. And we get 178 food calories. Now that would be equal to 178 kilocalories. Just to keep on going with that, we don't have to. 178 kilocalories, KCAL. Trying to write here, KCAL. And that would also be equal to 1.78 times 10 to the 5th little calories. Okay. All right, on to changes of state. So we're going to talk about like this is water, and the water is going to be melting on a block of ice. So when water melts, when ice melts when it reaches the temperature of 0 centigrade, and then it produces water that's at 0 centigrade. So the temperature doesn't really change when it's melting. How much heat is needed to melt a solid? Well, you notice we have no temperature change. So this is the formula that we normally had before, mass times temperature change times specific heat. But since we don't have temperature change, we're not going to have specific heat either, but we need another factor because not every substance needs the same amount of heat to melt. And that other factor is called the heat of fusion. So there'll be a chart with these heat of fusions in it. So the heat of fusion is the energy, it's per gram, I think we'll be using it to figure that out. And for water, it's 80 calories per gram. So water and ice meaning the same thing. So that means if you had 1 gram of ice and you wanted to melt it, as long as the ice is already at 0, it would take 80 calories per gram. If you had 10 grams of ice at 0, it would take 10 times that, or 800 calories per gram. So why don't you solve this one? Pause the slide, pause the show, and try it on a piece of paper, and then come on back and check the answer. Okay, here we go. Here's our formula, mass times heat of fusion. Plug in our values, 15 grams of ice, 80 calories per gram of ice, and we get an answer of 1,200 calories. Pretty easy, pretty straightforward. Okay, now we're talking about water boiling. So you notice we have a Bunsen burner down here. We have water in a beaker. We got a thermometer in here, and we're reading it 100 degrees, the boiling point of water at normal pressures. Now, does the temperature of water change as it boils? So, like if you were heating water on a stove, let's say you're boiling some food, cooking pasta. Does the temperature of the water continue to rise as you heat it? So is the temperature higher after you've been heating the water for 10 minutes? Let's say after you've been boiling it for 10 minutes than it was when you had boiled it for 5 minutes? And the answer is no. Because once you reach the boiling point of water, the energy that you put into the water is now used to convert the water to steam. It's not used to raise the temperature of the water anymore. So that means that under normal pressures, water would never reach a temperature higher than 100 degrees centigrade. But once you make the steam, now the steam can further absorb more energy and have its temperature go up. So to figure out the energy needed to change water to steam or have steam condensed to water, we have a very similar formula that we had a moment ago, only instead of heat of fusion, it's heat of vaporization, which is a much bigger value. Look at it for water now. 540 calories per gram. That means it takes that much heat to change 1 gram of water at 100 degrees centigrade to steam at 100 degrees centigrade. Whereas to melt a gram of ice, it took only 80 calories per gram. Okay. So let's do a problem where we use that. So how many kilocalories are needed to change 50 grams of water at 100 degrees to steam at 100? So we're going to say heat equals the mass times the heat of vaporization. Now, because I want kilocalories, I have to throw in this other conversion factor down here. So 50 grams of steam. This is the heat of vaporization here. 50 calories per gram. And if it was another substance instead of water, it'd be a different number. And then is our conversion for calories and kilocalories. We'll get an answer of 27. And this is a heating curve that you would have if you started with ice at the bottom, ice down here, let's say. And it could be any pure solid, really, because you notice they don't put any, there's no temperatures listed on here. So you have ice down here, and you heat the ice, you bring it to the melting point, which would be 0. And then all along, it stays at 0 as long as you have ice and water. Once all the ice is gone, continued heating will change the temperature of the water up to the boiling point. So for water, that would be 100 degrees. But then you see the temperature stays constant as you're going from water to gas. Once you've made all that steam, its temperature could further rise. Now this is a cooling curve, which just looks like the opposite of that heating curve. So if you started with steam at 140 degrees and let it cool, it would stay as steam as it lost heat. 540 calories, well actually it's a different amount. Once it became at 100 degrees centigrade, that steam then condensed to water and release 540 calories per gram. Now right here it's all water. Now that hot water at 100 degrees can continue to lose heat to the air. And if it's a cold day outside, your temperature could probably reach 0. Once all that water becomes 0, it'll start to freeze. And so you'll have water and ice at 0 degrees. And then now this would be all ice. And the ice temperature can continue to drop. So the heating curve and the cooling curve like mirror opposites. Okay, and that's the end of the show.